Hi, good day to you, and welcome to my channel where I tutor you in science for free. The topic in this video will be magnetism. And magnetism is a pretty simple chapter and a short one in fact, and it should be pretty easy to grasp because a lot of magnetism has been taught in like lower sec science, primary school science. It's not something extremely foreign, but it does lay the groundwork for the following few chapters. Very basic stuff, properties of magnets, like poles will repel and like poles will attract. If you freely suspend a magnet, it will point its north pole of the magnet towards the north pole of the Earth. That's why the notation on the magnet is that the north pole of the magnet will face the north pole of the Earth. And magnets always have two poles. So if you take one piece of magnet and you split it up into smaller pieces, each of these smaller pieces will also have their two poles. And as a magnet, it will attract magnetic materials. In a magnetic material, there are magnetic domains whereby they point in a certain orientation. If the domains are not aligned, it is not a magnet because it does not exert a uniform force around. However, if all the domains, magnetic domains, are aligned, then the magnetic material has become a magnet. It is said to be magnetized because all of them will act in a certain uniform direction. And a very common phenomenon will be induced magnetism, which means to say a magnetic material, upon attraction to a magnet, it itself will become a magnet. And why is that so? Because all the magnetic domains are now being influenced at that period of time, at the instant, with the magnet. Therefore, it itself becomes a magnet. This is the principle of how a magnetic material can be magnetized by stroking, because the domains follow the magnet along the stroking pathway, and through multiple times of stroking, the material will have its domains nicely aligned. Once it's aligned, it exerts a force on a certain region, and this region is called the magnetic field, the region where the force of magnetism will act upon, and be it in a bar magnet or a solenoid. A solenoid is just a coil of wire. That brings us to our next topic, which is called the right-hand grip rule. The right-hand grip rule talks about identifying the north pole of the solenoid, with the understanding from earlier chapters talking about current electricity. If the current flows in a certain direction, you use your right hand. Okay, you place both hands like that. The one that shows an L is the left hand. You put that aside, you only want the right hand. Okay, so now you follow using your four fingers and trace the current along the coil. The resultant direction the thumb is pointing at will be the north. So that is for the solenoid. So we have talked about magnetic materials and having magnetic properties. What about if we want to remove the magnetic property? That's called demagnetization. These are some couple of ways to do it, and all of them have the common objective to remove or mess up the magnetic domains, make them point in all directions so that a magnet is no longer a magnet, it's just a magnetic material. So place the magnet in the east-west direction and heating it, this will cause the domains to be messed up. Placing it in the east-west direction removes the Earth's influence on the field, making the demagnetization more effective. Dropping your magnet on the floor as well is akin to hitting it or hammering it. Another method is to use alternating current, which we will learn in the future video. And alternating current means that it changes its direction of flow as the AC motor moves every half a turn. And because the solenoid changes its north and south pole frequently, it will help to mess up the domains of the magnet. And of course, placing it in the east-west direction, slowly pulling it out to help it experience the messiness of the poles of the AC solenoid will help to mess up the domain of the magnet. Therefore, demagnetization happens. As a result, to keep the magnetism of magnets, we use keepers, which are just a magnetic material, and to keep it in place, to keep the magnetism flowing. Magnetism does not get used up like a battery or coming into contact with another magnet, but over time, magnetism do get lost over time due to external factors like magnetic field, temperature, or having magnetic items around it over the course of time. So we talked about magnets having magnetic properties, how to demagnetize something. That leads us to the next topic of temporary and permanent magnets. So temporary magnets are ones that will exert their magnetism only in the presence of an electric current. However, permanent magnets do not require such as systems to retain their magnetism. To choose the material for the temporary magnet, we need what we call a soft magnetic material, which is probably an iron, because it's easily magnetized and demagnetized, so you can magnetize it upon command. On the other hand, if you want a permanent magnet, you need a hard magnetic material like steel. So these are just common examples, and they are the opposite of the soft magnetic material. It's difficult to magnetize and demagnetize. So if you want the property to be there for purpose of digital devices, electronic devices, then the right material to choose is a hard magnetic material. And because soft magnetic materials, they gain the magnetism fast, they will become stronger induced magnet. These are some other elements that make magnets, but the common one is generally iron, and these are non-magnetic materials. And next topic, we'll be talking about some fun, engaging activity, that is the magnetic field lines. Usually we have to draw them out. Magnetic field lines are shown when we sprinkle iron filings around a magnet. Then the filings will fall into a certain formation. These formations look like lines, and the lines congregate at a certain area and they space out at certain areas. These are called the magnetic field lines, and they are drawn usually with the lines, the arrowheads, pointing out of the north and entering the south. They never cross each other, continuous, and they form loops. Distance between them show the strength. The closer the lines, the stronger the magnet. So a common exercise is to use a compass. A compass has a magnet inside to trace the magnetic field lines. So if the magnetic field line is equally spaced, so this what it is called a uniform magnetic field. If it starts to disperse, it's non-uniform magnetic field. And these are some common ways to express attraction as well as repulsion. And in repulsion, it's good to identify this point over here at the middle. Is called neutral point because the resultant magnetic field in that region will be zero. They cancel each other. And here are some common ways to draw the magnetic field lines between bar magnets. So it's a good exercise to draw them out yourself to experience how is it like. And that's about it. We'll look at some questions. So like mentioned, it's quite a simple chapter. So of course it's not going to be as easy as the primary school version. Okay, figure shows magnetic field between North Pole, South Pole of two magnets. Lines are linear and parallel, evenly spaced. What does this say about the magnetic field at X? This shows that it is uniform, like mentioned earlier in the video. So next question will be, lines are further apart. What does it tell you about the magnetic field? It's non-uniform, and region Y will be weaker. So state what is meant by North Pole. When freely suspended, North Pole points to North Pole of the Earth. Describe an electrical method to demagnetize a bar magnet. You may include diagram in your answer. So good to draw an image out when you see this kind of instruction. What we covered is to use the AC alternating current, because every half rotation of the motor, the direction of the current, electrical current changes. So placing the bar in the east-west direction of the earth and in the middle of a solenoid carrying an AC. So as the AC is running, remove the magnet out of the solenoid slowly to allow the magnet to experience the changing of the poles of the solenoid. Okay, figure shows iron ring suspended by a thread. Bar magnet held close to the ring. Iron ring is attracted to magnet. Explain why the iron ring is attracted to the bar magnet. So a lot of this is about phrasing, about description, about communication. We all know the theory, but we need to be able to talk about it properly. So the magnetic pole of the bar magnet has induced the iron ring, which is a magnetic material. The side of the ring that is nearer to the bar magnet has become a south pole, because the north pole of the bar magnet is pointing towards the iron ring. However, and as a result, the other side of the ring becomes a north pole, because unlike poles attract and like poles repel, the force of attraction is greater than force of repulsion. Therefore, the ring is attracted. And that is all for today. Hope you enjoyed this video. Do give it a like and subscribe, and share it with somebody who needs to see this. And I will catch you in the next video. Bye!